Yeah. Yes. So let me just quickly introduce you. Everybody, of course, who's doing electrochemistry knows him very well. He did actually his bachelor studies at Xiamen, and then for his PhD he moved to Washington University to work with one of the heroes, of course, of the big renaissance of electroorganic chemistry, Kevin Möller, who's also featured in this volume, of course. After a postdoc until 2013 with John Ellman, he moved back to Xiamen University and has really stellar trajectory in his academic achievements, which largely focus on synthetic electrochemistry. And today he will talk specifically about the topic of photoelectrocatalysis in the next roughly 25 minutes. So the stage is yours. You may start.
All right. Thanks, Luz, for the introduction. I hope, can you hear me?
Yeah.
Okay. All right. That's great. Also, I want to thank Thieme Chemistry for putting together this very exciting seminar. So as a group, we've been interested in the chemistry of radical intermediates over the past few years. Actually, in my whole independent career, we've been developing various electrochemical methods to produce different types of radical intermediates. Then we study the reactions of these intermediates to build carbon-carbon, also carbon-heater atom bonds. So over the years, we studied different types of radical intermediates. So traditionally, the radicals under electrochemical conditions, the radicals are produced on the electrode through direct electrolysis. So these radicals are produced through either oxidation or reductions on the anode or cathode. But there's some limitations associated with these methods. So recent years, we and others, we've been trying to develop catalytic methods using a redox catalyst to do the electron transfers between the electrode and your substrates and to produce radical intermediates. There are a lot of methods have been developed in the past, especially in the past few years. Probably we'll hear more in the coming talks. Also, these methods are very powerful. So these methods have been expanded the scope of electrochemically driven radical reactions dramatically. But also we've met some limitations also that's inherently very difficult to address with electrochemistry alone. So in the past few years, we've been trying to merging electrochemistry with photocatalysis, try to develop molecular photoelectrocatalysis to address some of these issues. And so today I'm going to focus on this topic. So under electrochemical conditions, even with catalysts, we have a very limited access to very positive or very negative potentials. And this is some of the catalysts that we commonly use in the laboratory to do radical reactions. You can see that their potentials basically lie in between 0.5 to about 1.5 watts. So it's very difficult to oxidize something that's, for example, benzene with this catalyst. And also, there are not that many catalysts for their reduction reactions also. Even if it can come out with catalysts that have very strong, very high or very low potentials, then you will have these selectivity issues, because at these very positive and negative potentials, you will have many side reactions. So there's another also, during our studies, we've met these over-oxidation or reduction reactions of radical intermediates. For example, for these very electron-rich radicals, carbon radicals, if you do oxidation reactions, because usually your radical precursors, for example, this trifluoroborate, is oxidized usually much higher than these electron-rich carbon radicals. So basically, if you can oxidize these precursors, you basically will over-oxidize these radicals to carbon cations. So most of the chemistry, electrochemistry, usually deals with this type of radicals, usually do the further oxidations to carbon cations. So if we wanted to do radical reactions with this electron-rich carbon radicals, it's very difficult. So with these difficult challenges, we wanted to introduce photochemistry to electrochemistry, so to solve some of these issues. So we combine electrochemistry with molecular photocatalysis. We hope to access very high oxidizing or reducing excited states with very large electron potentials. So we lower the electron potential, and also in the meanwhile we can do oxidize or reduce very difficult substrates. And also with these excited states, we hope to achieve different selectivity or even better selectivity from the electrode itself or the ground state catalysts. Of course, this idea have been put forward actually as early as late 70s and 90s, 80s. But did not receive much attention until very recently. Besides us, there's also other very exciting contributions from different research groups. So this, the chemistry we're talking about, the molecular photoelectrocatalysis, is different from traditional interfacial photoelectrocatalysis. In this chemistry, the photoabsorber is the semiconductor photoelectrode. So you use a very special type of electrode. For the molecular photoelectrocatalysis, the photoabsorber is the molecular catalyst. So this catalyst actually absorbs light to do the catalysis. So in the literature, you will see that very often it's also called electrophotocatalysis. It's a different name for this chemistry. There's some very exciting reviews on this topic. If you're interested, they're very recent from the Thieme Group on JAX, and also this Beijing also published 2 reviews on this topic. So of course, the chemistry we first studied, it was not easy to do because there are several challenges with this topic because you have to combine electrochemistry with photocatalysis. There are not that many literature that you can follow how to do this. So eventually we came up with this simple reaction. This is the acylation of the heater rings with trifluoroborate. Here I want to mention that this reaction has been previously achieved by Professor Menander using potassium persulfate as the chemical oxidant. So here we used a photocatalyst, this Fukuzomi acridanium photocatalyst, in this as a photocatalyst to activate the trifluoroborate. And this is done with the in acid nitrogen water at room temperature. We add the TFA just to increase the activity of the heater cycle. So this is done with a constant current with a very low current density, also, with the blue LED irradiation. As you can see, the control conditions. So under these conditions, we can get a good yield of this product, of the acylation product. And the photocatalyst, light, and electricity are all essential for these reactions to occur. This is the setup we use. This is very, it's a simple setup, but you see that here we use a light refractor just to increase the efficiency of the photochemical step. Because the challenge with this chemistry is that usually the photochemistry is slow relatively to electrochemistry. So usually we have to increase the efficiency of the photochemical part of this process. So with this chemistry, we now can do the radical reactions or these very electron-rich radicals. For example, this tertiary carbon radical can react efficiently, and also this carbon radical with the oxygen next to it. So these are very electron-rich radicals. Usually under electrochemical conditions, you will over-oxidize these radicals to carbon cations. But here, we can do these radical reactions very successfully. So this is the first reaction we did, and we didn't actually study much of the mechanism. We just proposed the mechanism based on literature data and also on thermodynamics. So upon photoexcitation of this acridanium catalyst, it produces this very highly oxidizing acridanium ecstatic state. So with a reduction potential about 2 volts. This is a very strong oxidant. So it takes the electron from trifluoroborate. This is oxidized at about 1.3 volt. So thermodynamically, this is a very efficient process. So you produce the T-butyl radical and also a reduced catalyst. So this acridine radical, this is a stable radical. So it has enough lifetime to travel to the anode to get oxidized back to the ground state catalyst. So for the T-butyl radical, this is produced in the solution phase. This is also a transient radical. It's very reactive. So it reacts with the protonated heterocycle to produce the nitrogen radiocation. So this is an acidic radiocation. So it loses a proton to produce this carbon radical. So the carbon radical is highly reducing, as you can see from the reduction potential of this heterocycle. So it's reduced at about 1.3 volt minus. So the oxidation potential of this radical can be estimated close to this potential. So we think that this radical, the carbon radical, it's oxidized by the ground state catalyst. Thermodynamically, this is possible because the reduction potential of this ground state catalyst is about minus 0.6. So it's thermodynamically feasible to do this. But of course, we didn't study this process. We just assume that's possible. So you get the product. So here the key is that you, in this chemistry, most of the energy for this reaction is provided by blue light. So you can keep a very low electron potential, just enough to oxidize this acridine radical. So very low electron potentials. So you can avoid over oxidizing many of the intermediates or products or substrates. Also wanted to point out that this T-butyl radical is produced in the solution phase, and also it's very it's a transient radical, so it does not have enough time to travel to the electrode, so it will not get oxidized by the electrode. And also, because of the photocatalyst, the excited state is also have very low lifetime. This is about 10 nanoseconds. So the concentration of this excited states is very low. So also electron transfer between the excited catalyst and T-butyl radical will not occur. So under these conditions, you can avoid over-oxidation the electron-rich radicals, and you can do the radiochemistry. So this is the key success to this chemistry. I wanted to point out that in very similar time that there are also other contributions from other research groups. For example, Professor Stoll and Professor Neber, they independently reported different approaches to this photoelectrocatalysis. They developed methods to do the CM bond formation reactions. So from there, we've been trying to develop a method to use the carboxylic acids as the active radical precursors, because these compounds are much more easy to obtain, and also they are all stable. So it's highly desirable to use these carboxylic acids as active radical precursors. As you can see, I also see many studies in the literature using photochemical methods. The challenge to do this chemistry with the carboxylic acids for the mini-site type of calculations is that the reaction requires acidic conditions to increase the reactivity of these heterocycles. But usually to activate the carboxylic acids, you usually need basic conditions, because the carboxylate is much easier to be oxidized than the carboxylic acid. So we have this dilemma here. So we have to come out with conditions to activate the carboxylic acid under acidic conditions. Eventually, we're inspired by the studies in the literature on serine photocatalysis, particularly by Professor Zhou and Professor Koenig. So eventually, we were able to come up with this very simple serine salt as the photocatalyst to do this chemistry. With these conditions, we can work with various carboxylic acids, primary, secondary, and tertiary carboxylic acids. We can also do these reactions in grain scale. We produce these cyclohexyl products in about 13 grains. We can also do alkylations of some complex structures. So we started this mechanism using this cyclopropyl substrate. We observed this ring opening and then alkylation product. this suggests that we produced active radicals during the photoelectrochemical reactions. In the literature, we know that the actually photoactive state of the serine is not the serine 3 we add, it's the serine 4. So we have to generate the serine 4 during the reaction. So once we add the chloride to the serine 3 itself is very difficult to oxidize. Once you add chloride to make the chloride complex, you can see that the serine 3 to serine 4 are wave here. So the oxidation potential of serine 4 chloride complex is serine 3 chloride complex is relatively low, about 0.4 watts. So you can oxidize serine 3 to serine 4 very easily once you have chloride in the reaction system. This is why we need to add the chloride salt into the reaction system. So based on literature data and also our studies, we propose this mechanism here. So the chloride serine 3 complex is oxidized on the anode at about 0.4 watts. So to the serine 4 complex. The serine 4 is the photoactive complex. So it complexes with the carboxylic acid to produce this carboxylate complex. Upon photo excitation, it undergoes ligand to metal charge transfer to produce the serine 3 back, and also a carboxylate radical. So this radical decarboxylates very efficiently to produce a acute radical. So this then further undergoes acylation and deprotonation to produce, once again, this very electron-rich carbon radical. We think this radical is oxidized by serine 4 in the solution to produce the follow product. So here, the active photocatalyst actually produced through anodic oxidation and then do further reactions. And also, I wanted to point out that we can now do decarboxylations at very low electron potentials. It's much lower than the carboxylic acid itself. So we can do we can provide the energy with the photo irradiation. So from here, we ask the question: can we control the stereochemistry of these radical reactions under these photoelectrochemical conditions? Because currently there's no method in the literature to do this. So we studied a lot of many reactions. Eventually, only this one at that stage, only this one was successful. Is the CH cyanation of the benzylic CH bonds. So this reaction has been previously achieved by Storr and Liu. They developed this method using copper catalysis with a stoichiometric amount of NFSI as the oxidant and also as the hydrogen atom transfer agent. So this the ecobenzene undergoes HAD to produce the carbon radical here. Then it reacts with the copper complex to do a ligand transfer to produce the cyanation product. So we figured that we can come up with a photoelectrochemical method to produce this radical and also use the same copper complex probably to achieve the asymmetric cyanation reaction. So we studied various catalysts. Eventually, we come up with this androquinone photocatalyst with two sulfonate groups on the benzene ring. And also, we used this box ligand here as the ligand to control the stereochemistry. And this ligand has been developed by one of our speakers, Professor Ning. They have used this ligand for electrochemical asymmetrical cyanation reactions. And this turned out to be the best ligand in our studies. So we have do a lot of control experiments. Without light or without the photocatalyst, we basically cannot get the product. And also electricity is very important for this reaction. And also we can do this in grand scale to get good yield of the cyanation product. So this chemistry is turned out to be very selective for the benzylic position. Even if you have two benzylic sites, this goes selectively, very selectively actually, to the more electron-rich benzylic site So here you can see that between these two arrow groups, the difference is that there's a T-butyl group on this phenol ring, but you get an exclusive reaction at this benzylic site. Also, this goes to the secondary benzylic site instead of the tertiary benzylic site. Also here, you have electron deficient pyridine ring and also a phenol ring. This goes to the more electron-rich site. Between benzylic sites and propagenic sites, and also benzylic sites and allylic sites, this is also very selective for the benzylic sites. So it's not only very selective, it's also very inclusive. You can see here the reaction towards these acrobenzenes of various electronic properties. So the azobenzene with electron deleting groups are compatible with this reaction, and also halogens, and also very electron withdrawing sulfonamide or this carbonyl ketone group. But of course, this cyanyl substrate, this is probably too electron deficient. The conversion of this substrate is very low, so we get low yield. So oxidation potential of this is probably too high for this reaction to proceed efficiently. We also try to functionalize some complex substrates to show the compatibility of this method for complex structures. You can see here that with many tertiary CH bonds, the selectivity for these benzylic sites is very good. We also did some other substrates. For this, I want to point out this gabaridic acid derivative. You can see that there are several CH bonds. For example, this allylic CH bond here, and also this allylic CH bond also alpha to the alcohol here. These CH bonds are very weak. They're much weaker than the actually the benzylic site CH bonds. So still, we can have very good selectivity for the benzylic CH bonds. So I wanted to point out to the proposed mechanism first, that I can show you some evidence that we have for this mechanism. So here is the catalytic cycle for active with the CH bond. So the photocatalyst is excited to produce the excited state. So this undergoes electron transfer and then proton transfer to produce the benzylic reactor. This is different from literature. Usually the literature, they usually use hydrogen atom transfer, but this goes from electron transfer followed by proton transfer. And the following steps, this is established in the literature, is the reaction of the carbon radical with the copper-2 complex to produce a copper-3 complex. This then goes in anti selective reductive elimination, to produce the final product. So the copper-1 complex and also the reduced androquinone catalyst are oxidized back to the ground state catalyst, or the copper-2 on the anode. So how do we know this goes from a stepwise mechanism to cleave the CH bond? So we studied this very closely. The first, we wanted to see if prove that they are radical produced. So we use this allosulfone as the trapping agent. We can see under the standard conditions, we can produce these allylation products. So you will see that this is actually produced a carbon radical. And also without electricity or copper, we can still see the product here. So this tells you that the carbon radicals produced only need the photochemistry, not electricity or copper catalyst. So we also use these two special substrates, this alcohol and this solar substrate. Under these conditions, we see the cleavage of the CC bond, also the silicon bond. So this tells you that this is not a HAT process. Otherwise, you will not be able to see the cleave of these bonds. So this tells you this is a stepwise electron transfer followed by proton transfer. So once you produce the radical cation, this can cleave either the CH bond or CC bond to produce these radical intermediates. Eventually, you will see the products. For the carbon silicon bond, this is much easier to cleave than the CH bond. So you produce this benzyl cyanide exclusively. And also we did a Hammett plot analysis. This is consistent if you get a very negative and minus this role. So it suggests that accumulation of positive charge during the transition state of the rate limiting step. What's puzzling is that we also observed a primary KIE for this process. At first glance, you would see that this is a HAT process. It's not consistent with the electron transfer, but actually we can come up with a reaction model that's to explain this. The model we came up with is this kinetic model is that the electron transfer step for this ecstatic state catalyst with the acobenzene is reversible, and then followed by irreversible proton transfer. With this model, of course, we assume steady state approximation for this iron pairing formation. We can come out with this rate constant. From here, you can see that both electron transfer and proton transfer are involved in this rate equation. So you can see that both of the electron transfer and the proton transfer will affect the overall reaction rate. I want to point out that Professor Liu also reported similar chemistry very recently on Chem Archive. They use a slightly different catalyst for this photochemistry. They propose that the reactions goes through hydrogen atom transfer instead of electron transfer. The difference is that our catalyst is very electron deficient with two sulfonate groups. So this catalyst has a much higher reduction potential than the angioquinone itself. So this electron transfer is preferred for our chemistry. So because the carbon radicals formation and also the following reaction are independent with two catalytic cycles, so we can imagine that we can use other precursors to generate the carbon radicals. Here I show you that we can use the carboxylic acid as the precursor. We generate the radical, and then we can do the same cyanation reaction. So we can do decarboxylative cyanation reactions with photoelectrochemistry. So that I'm showing that molecular photoelectrocatalysis is actually a very versatile platform to expand the scope of these radical reactions. So we can not only do selective radical reactions, we can also now control the stereochemistry of the radical reactions. With that, I want to thank my students, postdocs, collaborators, and also the funding agents for funding. And also wanted to thank you for your attention. I thank you very much.
Yeah, thank you, Haichel. Great talk. Are there any questions? Please feel free to ask them either, well, mostly in the chat if possible. Otherwise, I will start with a, I have a few questions, so really great work.
Thanks.
But I'll share my webcam. Okay, I can share my webcam, I guess. Anyway, I was wondering, so one is semantic and one is more conceptual. One conceptual question is, you mentioned the kinetic photo versus electron transfer, and they are significantly different. So in terms of the bilayer, the Helmholtz layer, how much do you see the dependence on the efficiency of the photoelectrocatalysis based on the electrolyte and anode material?
This is a great question. Usually we on this on the electron material, we did most of our reactions with the RVC, is the with the high surface area carbon electrodes. Basically, we need to keep a very low. In our to keep, basically, we need to keep a very low current density for this reaction to be efficiently. Essentially, in these reactions, of course, actually you oxidize the species here, the reduced catalyst. Their concentrations are actually not very high. You can imagine there's low concentrations. So you don't want to have a very high current density, then you don't have anything to oxidize. You will oxidize something, right? You oxidize your substrate, your product, or other things. So that's why we use this RVC with a high surface area. This works best, at least for our reactions. We also, of course, of every reactions, we screen the electron materials. They are important for us. And also on the electrolytes, they are also important for some reasons, which we don't fully understand. For most of the reaction, we screen different type of electrolytes, but of course, mostly we use the tetraacyl salts. Some of the, for example, for this ionic catalyst, photocatalyst, the salts, they can also influence the redox properties of the catalyst.
And then maybe a short semantic question, very clear talk. So how do you feel about photoelectro versus electrophoto chemistry of catalysis? Do you see it as a semantic, or is it important to you?
For me, this is a good question. Actually, you can see in our publications we actually use the both, here and there. For me, I think they're the same. But of course, you use electrophotochemistry. It's probably easier to distinguish from the traditional photoelectrocatalysis. You don't have to. But I have to be frank with you that we, at least in some of my recent publications, some of the reviewers they're not they say it's better to use photoelectrocatalysis. So different people have different opinion, but I think the chemistry itself they're not that different. They tell the same thing, but just different. You switch the position of photo or electro. I think they're both okay with this chemistry. Yeah.
Okay, fantastic. No, really a great talk, and
thanks.
I guess there are a couple of questions in the questionnaire. So there are more questions in the questionnaire, I guess. Let's see, maybe I pick one. When the carboxylic acids are used, do you observe any Kolbe or non-Kolbe products? So I guess,
that's a good one. Yes. So let me show you that actually this is actually for the reactions that we did. It depends on the radicals. You can see here, if I show here, it depends on really the radicals you study. For most of the radicals we study, we don't see that. But there's one type of radical that's very electron rich one. So if I have a nitrogen next to the carbon, that's very electron rich. This is the oxidized probably close to 0. So you can see the serine is oxidized at about 0.4 volts. So in those cases, you do see overoxidation to carbon cations. But for others, they are not very significant. It depends on the catalyst you use. For this system with this system, you don't see that, because you can see that the ground state catalyst is not a good oxidant. But serine itself, serine 4, it can be oxidized. It can oxidize some of the carbon radicals. Yeah.
There are more questions about the setup and biologically active compounds. So maybe feel free to answer them in the question and answer, or maybe let me see. There's a specific one on slide 15. Can you explain what is NFSI and its role in the reaction? So maybe that's for the understanding of some listener, and with that, then we.
Could you repeat which slide?
I guess he wanted to know the acronym for the NFSI here. Maybe it's good to appreciate the importance of your work to again explain what is NFSI and how you can replace it, I guess.
Yeah, I guess here we just NFSI is here is both the hydrogen atom abstractor and also oxidant to oxidize the carbon radical. Our chemistry goes from a slightly different mechanism. It's not HAD. It's a proton electron proton transfer. And also, if you read Professor Liu's work in Conn ICAF, you will see that the photoelectrochemical method the substrate scope is much higher, much better than the NFSI studies. So you can improve the substrate scope with the photoelectrochemical methods.
Yeah. No, that's really amazing. So yeah, congratulations for your nice findings also on the asymmetric transformations. And with this, I think we all applaud virtually Professor Haichao Xu for his nice presentation, and continue with our second talk before we make a very short break. The second talk will be, so thank you again, Haichao, and